let us look at how to calculate the tolerance range of resistors. All right. But before then, I would like to answer one of the questions I was asked in a previous lesson. And that question is that why is it that some colors are not assigned tolerance values on the color band? All right. For example, looking at the standard color code that we have here, we see that black doesn't have any tolerance value attached to it. Same thing goes for orange, for yellow, and for white. Okay, recall that at the beginning of this discussion, we tried to answer an important question, and that question was why do we use color bands instead of printing numbers on the resistors? Okay, and one of the answers we got for that is that the color system is standardized worldwide based on the IEC standard. All right. The IEC is the International Electrotechnical Commission, all right, which is responsible for the manufacture, standardization of some electrical of many electrical components. We also have the NEMA, we also have the IEE. So there are worldwide standards that defines how these components are specified and manufactured. Okay, so based on IEC standards, the black color does not have any tolerance value attached to it. Same thing goes for the orange, yellow, and white. Okay, now recall that we said these colors can play any role on the resistor based on the position of the color on the resistor. All right, any color can act as a digit, as a multiplier, or as a tolerance based on the position on the color on the arrangement of colors on the resistor. Now, for black can act as a digit, black can act as a multiplier, but black does not act as a tolerance. All right. Same thing goes for orange. Orange can act as a digit, as a multiplier, but not as tolerance. All right, and also yellow and white. This is based on what is defined by the IEC 60062 standard. Just like we have the SI units, SI system of units that defines how quantities are measured. All right. Same thing goes for the IEC standard, the IEC, the NEMA, the IEE, and all of that. These are standards that defines how these components are manufactured and then the specifications that they are given. So I believe that answers the question as to whether some of these colors can still have tolerance or not. Okay, now how do we calculate the tolerance range of a resistor? Tolerance tells you how far the real resistance may vary from the nominal value. So what now is the nominal value? Let's first of all explain what this nominal value is. Nominal value, all right? The nominal value is the actual value calculated from the color bands. Looking at this example, we have a 5-band resistor here, all right? And when we have a 5-band resistor, the first 3 bands represent digits. The 4th band represents the multiplier, while the last band represents the tolerance band. Okay, but if it is a 4-band resistor, the first and second bands represent digits. The third band represents the multiplier, while the 4th band now represents the tolerance band. Okay, so looking at this 5-band resistor, we can easily tell the resistance value. We can calculate it based on our standard color codes. Okay, so if we apply the standard color codes, here we are saying that the first 3 colors here are digits. We have brown, black, black. So brown from the standard color code is 1. All right, brown is 1. Let's write that here. Then, beg your pardon, yeah, brown is 1. Then black is 0. And we have 2 blacks there, that's 0, 0. Okay, looking at the standard color codes. All right, brown is 1, black is 0. So these are serving as digits based on their position here. All right, the first three bands on the 5-band resistor are digits. Then the next one, which is the fourth band now, is the multiplier, and we have red. Now, when red is serving as a multiplier, all right, red in this case is not serving as a digit. It's not serving as tolerance. It's serving as multiplier because of its position. All right, so the multiplier here is 10 to the power of 2. So going there, we have it that the multiplier now is going to be 10 to the power of 2 times 10 to the power of 2 ohms. So that is the resistance value now. Now, the tolerance is the last band, and it is brown. And we have said that brown has the value of, 1 when it is serving as a digit. Okay? When serving as a digit, brown has a value of 1. But in this case, because it is having, having a position here, the last position here now, that means it's serving as a tolerance too. All right? Here is serving as a digit, here it's serving as tolerance. So when brown is serving as tolerance, the tolerance value is plus or minus 1%. All right? Kindly take note, it's not as if the tolerance value must coincide with the digit value. All right? If you check some other colors there, like yellow now, or like green now, you can see green acts as 5 when it is a digit. But tolerance is going to be plus or minus 0.5%. So it's not that the digit will always coincide with the tolerance value. All right. This is just what IEC has defined. Okay. So when brown is acting as tolerance is plus or minus 1%. So we go there, we have it that the tolerance here now is plus or minus 1%, plus or minus 1%. Okay. 1%. All right. So what then is the nominal value? Recall that I want to understand what nominal value is. The nominal value, I beg your pardon, is this value now that is calculated, which is 100 times 100. 100 times 10 to the power of 2, all right? That will give us 10,000. 10,000. 10,000. 10,000 ohms. 10,000 ohms. So 10,000 ohms is the nominal value. The nominal value, all right? Then you now bring in the tolerance value, which is 1%, plus or minus 1%. So when you hear the term nominal value is referring to the actual value calculated, right, from the color band, exclusive of the tolerance, right? And now we are saying that tolerance tells you how far the real resistance may vary from the nominal value. The real resistance in this case is what the resistance actually is when you measure it. In the laboratory, you can use your multimeter, all right, to take readings of resistance, to take resistance readings. Sometimes you might see a resistor with a particular color band and you expect that, like this one now that we're having it as 10,000 ohms now. It is expected that when you measure it in the laboratory, you should get 10,000 ohms. But many times, you might not have 10,000 ohms. You might have something slightly below 10,000 ohms or slightly above 10,000 ohms. That is where this tolerance comes into play. So what you are actually measuring is the real value. It may coincide with the nominal value. I beg your pardon. It may coincide with the nominal value. It might not coincide, all right, with the nominal value, all right? So the degree to which it can vary is what we call the tolerance. And how do we get this tolerance? All right. Here, the example that we are citing here, the nominal value is 10,000 ohms. And then the tolerance is plus or minus 1%, right? So if we want to understand that better, that means if we take 1%, what this means is that this resistor value, the resistance value here cannot vary beyond 1%, either positively or negatively from the nominal value. That's a straight way to put it. So for us to understand that, we have to first of all calculate this percentage of the nominal value. So 1% of that nominal value is like saying 1 over 100 multiplied by the nominal value, which is 10,000. All right, this is 10,000. So 1 over 100 times 10,000 will give you 100, right? So that means this resistance value that we have calculated is like saying 10,000, all right, plus or minus 1%. The 1% here now of 10,000 is what? 100, which you have calculated, all right, plus 100. Beg your pardon, let's put the ohms there. Let's always ensure that our units are stated very importantly. So this is 10,000 ohms plus or minus 100. And that 100 is a 1%. Okay, is a 1%, all right? So what this means is that you can have, this implies that you can have 10,000, all right, plus 100 or 10,000, all right, minus 100. That's what this means. So therefore, the tolerance range will now fall between whatever you get here and whatever you get here. All right. So whatever you get here is going to be the maximum limit. Whatever you get here is going to be the minimum limit. All right. So 10,000 plus 100 will give you 10,100. All right. 10,100. And then 10,000 minus 100, I beg your pardon, this is 100 here, not 1,000. Okay. 10,000 minus 100 will give us what? 10,000 minus 100 will give us 9,900, right? So in reality, what this means is that this resistance value I've calculated can fall within this range. All right. So the range of value here means that it can range from 9,900 as the lower limit to 9,900 ohms. All right. To 10,100 ohms. So this is the range of values. Now this is what we now call the tolerance range. All right, there's a lower limit and then there's an upper limit, the minimum value and the maximum value based on, the tolerance value. All right, and you get the tolerance value from the last color band. To quickly mention, for gold and silver are usually used as tolerance bands. All right, they rarely, you will hardly find a resistor where gold and silver are acting as digits. And this is all based on the IEC standard that we have seen. Okay, so this explains how to get your tolerance range. Now, a simple formula can be applied based on mathematics, simple mathematics. Okay, so if you want to calculate your tolerance range, you can use this formula. The minimum value is going to be equal to the nominal value multiplied by 1 minus tolerance. Then the maximum value is going to be equal to nominal value times 1 plus tolerance. It's exactly what we have done here now. All right. If we plug in these values, this value now, 10,000, which is the nominal value, and then 10%. All right. If you are using this formula, you are going to be putting the tolerance in the percentage form. All right. So if we plug it in, we are going to still have the same results here. Let's take that example. Let's just plug it in and see for this particular example that we have seen. All right. For this 5-band color resistor here, or 5-color band resistor. All right. I beg your pardon, 5-band. Okay. So we said if we want to get the minimum value, it's going to be equal to the nominal value. So minimum value is equal to nominal value. What's the nominal value that we calculated? 10,000, right? 10,000 into 1 minus tolerance. The tolerance is 1%. All right. 1% is 0.01. Okay, so that will give us 1 minus 0.01. So when you are using this formula, the tolerance you are putting here is not going to be this 100, all right? It is that percentage that you are going to slot in here. Okay, so 1 minus 0.01 multiplied by 10,000 is going to give us 9,900. All right, so 1 minus 0.01 gives us 0.99. All right, so we have it that this will now be equal to 10,000 into 0.99, and that'll give you 9,900 ohms. So you can see that if we're using this formula, all right, we're still going to be arriving at the same value. This is the minimum value. Now the maximum value is going to be equal to nominal value times 1 plus tolerance, all right? So that's that for that. The example used here is a case of 47 kilo ohms plus or minus 5%. Okay, so 47 kilo ohms is 47,000 ohms. 47,000 ohms. All right. So if you plug in this value into this formula, you're going to be having the tolerance range for this particular example here, the one on this page now, as 47 ohms times this, and that will give you that. Okay. To clarify again, all right, when you want to calculate the tolerance range using this formula, the minimum value is going to be equal to the nominal value times 1 minus tolerance. The tolerance here is that percentage, all right? If the tolerance is 1%, all right, you put it as 1%. You don't need to say 1% of the nominal value, all right? You don't need to do it like that. 1%, just put it there as 1%. 1% is 0.01. But if you want to calculate it independently without using this formula, that's when you use this approach here. Plus or minus, 1% for this previous example means you take 1% of the nominal value, you add it and you subtract it. That is what this formula explains, right? So one tip here is that a resistor's measured value should fall inside its tolerance range. If it doesn't, the resistor may be faulty or out of specification. I just mentioned that in your laboratory, you can use a multimeter to check the resistor value. Now, if you see a 5-color band resistor like this, for example, and after doing your theoretical calculations, you discover that the resistance is supposed to be 10,000 ohms plus or minus 1%. That means, you are working with this range of values. When you now take a measurement with your multimeter or whatever device you're using to measure the resistance, the measured value should fall within this range. If it falls outside of this range, that means that resistor is actually faulty and is not functioning properly. All right. A simple way to wrap this up here is that this formula, all right, is obtained from this particular approach, this formula here. Minimum value is equal to, let's put it this way. Now let's assume that I have X as my nominal value, all right, plus or minus tolerance. Let me use T to represent my tolerance. My tolerance is in percentage, right? Is in percentage, plus or minus T%, right? So that means I'm having X plus T or X minus T, not so. This is going to be my maximum value. This is going to be my minimum value. So this T is a percentage, all right? T%. That is T% of X now, of the nominal value. So T% of X is like saying T over 100 multiplied by X. That's T% of X. So what I'm doing here technically is that I am saying that X plus or minus T% of X, right? Which is T over 100 multiplied by X. Not so. So that means I can have it as x plus t over 100 multiplied by x, or x minus t over 100 multiplied by x. All right. What I'm trying to explain here is that I'm just trying to use x to represent nominal value and t to represent tolerance. So you can see you can factorize this. This represents your maximum value. This represents your minimum value. So if I factorize this, I'm going to be having x into 1 minus t over 100, which is the tolerance. I beg your pardon, this is plus. Or here we can have it as x into 1 minus t over 100. So this is the maximum value, this is the minimum value. So this is like saying the nominal value bracket 1 plus the tolerance in percentage now, or the nominal value minus into 1 minus t over 100, which is same thing as what we are having here. Okay, so that's how to get the tolerance range of a resistor. Okay, there are a few exercises here that you can pause the video or screen grab and try to, try your hands on them. Okay, so the key takeaways here is that color bands encode resistors resistance value in ohms and its tolerance. All right, the 4-band resistors. For a 4-band resistor, the first two digits, beg your pardon, the first two colors are digits. Then the next color is the multiplier, and then the next color is the tolerance. The tolerance is often a little bit farther away from the other colors. Then if it's a 5-band resistors, the first three digits, the first three colors will now serve as the digits. The fourth color serves as the multiplier, and then the fifth color serves as the tolerance. All right, and then we apply the formula that we have seen in this explanation. So that's how to calculate the tolerance value of resistors.